Okie doke. So the plan today is sort of a two-headed lecture. So the first part we'll talk about gradient echo as opposed to spin echo. So we did all this stuff on spin echo. You might know that most fMRI experiments are actually gradient echo, not spin echo. So we'll talk about gradient echo, and then completely change topics and talk about the beginning of things relevant to the homework. So how do we get contrast? How do we get contrast between different tissue types? And so the very first thing we'll talk about is what does TR mean? So, and why is TR relevant? So that's sort of saturation recovery. The very simplest thing we can do is just do a series of RF pulses and look at the amplitude of the signal. So two completely different things. So we'll start off with gradient echo. So when you think about spin echo is kind of, I like to say, is kind of a morally upstanding echo. So when you do spin echo, you do an RF pulse, and then you wait some time, and then you do another RF pulse, and that RF pulse injects some more energy in there, but it then reveals a signal at a later point in time. So that you wouldn't have gotten that later signal if you hadn't done that extra RF pulse. And so that's kind of a good echo in a way. You do something else, and that sort of like helps you recover something that wouldn't have otherwise appeared. So gradient echo is kind of like sort of the poor cousin to spin echo, because with gradient echo, essentially what you do is you turn on a gradient, and what does the gradient do? Well, if you think about what a gradient does, it changes the B0 field. So, if we look at the X, I always draw the picture of the X gradient. So if you look at the happy person in the scanner from the top, and you turn on the X gradient, what does that mean? So here's the 0. If you turn the X gradient on, it means that if you're on this side of the person's head, you add that much to the Z, and you add less and less, and then if you're on this side of the head, you subtract from the Z. Now the actual Z is really big, so here's the Z. It's really big. You're just adding a little increment on top of it. And then so what does it mean? So say this is a positive gradient. What does it mean to have a negative gradient? A negative gradient just means, turn it on, the opposite way. And then what does it mean to have a stronger gradient? That just means, increase the slope of that change. So those are, so this is stronger. Oh man, this is a nice intense green here. This is negative. So that's the meaning of it. That's the meaning of a gradient. It just sort of changes the B0 field. But if you think about that, what does that do to the signal? Well, that's not good for the signal, because the whole idea of the signal is, if we want to get a big signal, we want to have everybody resonating at the same frequency. And so if you turn on a gradient, it's actually going to damage your signal. It's going to actually reduce your signal, because it's going to cause spins at different parts of the sample to resonate at different frequencies, and then they'll essentially get out of phase with each other, which means that when you add up all the vector sums of all of them, they'll cancel each other out. So gradient echo is kind of, if you have to summarize it in words, what gradient echo is you turn on a gradient, thereby damaging the coherence of the spins, and then you turn it on the other way, and you undamage them, and then you get back to where you would have been if you had done nothing. So that's actually, in words, what gradient echo is. So let's just draw out a sort of a typical sequence that you would do. So a sequence that you would do is, here's the RF pulse. So this is the RF. So that's RF stim. That's what you're actually injecting into the sample. And then here's the actual signal you get back. So right at the moment you inject the RF, what happens is you get a big signal like this. So if you hadn't turned the gradient on, let me erase this guy so that I have more room. Sorry, because I didn't have room for the gradient. So we need the RF, the gradient, and the result in the brain. Okay, so let's start again. So here's our RF. So that's the RF stimulation, and then here's the gradient. Now there's 3 gradients, but we'll just for the time being talk about the gradient, say gradient X. So immediately after we turn off the RF pulse, we turn the gradient on. Now you can't turn it instantly on, so typically there's a little bit of a ramp, so I'll draw a little ramp in. And so and then we turn it off. So that's a negative gradient. So, and what's that going to do? That's going to sort of mess up the spins. And then let's turn the gradient on positive for about the same amount of time as the amount of area here. So the critical thing is the amount of area under the gradient. So if you turn a gradient on for longer, that's equivalent to turning it on for shorter but making it steeper. So at this point, you can sort of see you're sort of gone back to where you were if you hadn't turned it on, and that's actually when the echo occurs. So now if we look at the signal, so this is RF stim, and then this is RF record. So here's the signal we get. So this is RF record. So if we hadn't turned the gradient on, then what we would get is what we described a couple lectures ago, which is just the FID, the free induction decay. So just like what happens if you don't do anything, just do an RF pulse and just, here's an alpha RF pulse, some random angle RF pulse. And what would you get? So what you would get is you would get T2 star decay. And so that would be something like this. So what is that? That's let's label it. So that's e to the minus t over t2 star. So what does that consist of? That consists of the T2 decay, which is jostling of other protons, the magnetic fields of other protons. And then it also includes the star part, which is extra decay due to the fact that there's some local differences in the magnetic field in different parts that are static. So if on this graph we drew the T2 decay is less. It's like that. So this guy is the e to the minus t over t2. And remember, that's what the echoes, the spin echoes were getting up to. They were sort of like getting up to the t2 curve. But now we've got 3 things going on. So we've got the regular T2 decay, and then we have extra star decay because even without the gradient on, there's slight differences in the magnetic field. And then we have T2 star decay because we turn the gradient on. And so what's going to happen is you'll get even sharper curve like this, a sharper decay curve like that. And that one we can call that one e to the minus t over t2 star star, because it's got static magnetic field offsets going on, but it's also got the gradient messing it up. So then what happens? So then we start turning, right here, we start turning the gradient the other way. So what's that going to do? So what that's going to do, so we start off with, this, signal like this. So here's our, signal coming out, and it's getting squashed down quite rapidly. But then we reverse the gradient. And so if we reverse the gradient, what's going to happen is it will start to repair the damage that we did. And so right around this point in time, the damage will get repaired. And so that means that we'll get back up to where we would have been on this T2 star curve. So basically, we'll get something that looks like this. So the signal will sort of like be extra crushed because we did it with the gradient, but now it's going to sort of be fixed. And then at this point, there'll be an echo. And so basically this is different than a gradient echo, than a spin echo. So in the spin echo, remember, we would have gotten all the way back up to the T2 curve because we were undoing the effect of the local static magnetic field offsets. Here, we're not fixing the static magnetic field offsets. And instead, what we're doing is all we're doing is just kind of repairing the damage that we did. We're just repairing the damage that we did. So that's the idea of a gradient echo. So it's kind of like when you first hear about it, it's just like, yeah, it's not a very good echo. It's kind of all you have to do is just not turn the gradient on, and then you would have gotten up to the same level that you got after sort of turning it on and messing things up, and then turning it on the other way and fixing things. So why do we do that? So the reason that we want to actually do a gradient echo is that there's another thing that a gradient does. And what a gradient does is it has to do with the Fourier transform. So a gradient, whenever you turn a gradient on, what you're doing is you're actually doing spatial encoding. You're actually setting up signals that, when added together, can essentially recover spatial location. So that's why you almost always want to have a gradient on. If you're recording any data, you're going to have virtually any data you're going to have a gradient on. That any data where you're trying to do any kind of spatial recovery of where the signal is coming from. So then it sort of makes sense that we would do this damage and undo the damage business. Now, you would typically leave it on, the gradient on, for sort of an equal amount of time. So once again, this decay curve is going to be faster than that. That's another e to the minus t, over t2 star star kind of decay. So that decay is again going to be faster than it would have been if you had left this gradient off. It would have just decayed along this T2 star line. So that's gradient echo, and with gradient echo, you can do pretty much the same thing that we did with echo trains. So you can have gradient echo trains. So in the case of spin echo, if you do, you would do like your RF pulse, and then after a while you would do another RF pulse, like the 180. And then you wait twice that amount of time, and then you do another RF pulse. So that's spin echo. Spin echo trains. And what happens is you get an echo sort of at this point, and then you get an echo at that point, and you can keep doing that and get multiple echoes. So you can pretty much do the same thing with gradient echo, except you're doing it with the gradient. So in this case, what you would do is you would turn the gradient on. So we'll turn the gradient on this way, and then instead of doing another RF pulse, you turn the gradient on the opposite way for twice the amount of time, like that. So one thing that's important to keep in mind with the gradients is that the RF pulse does everything all at once. You just hit it with the RF pulse, and the RF pulse will actually then very forcefully change the spins, and then they'll start to rephase. You don't have to continually do the RF pulse. The gradient is different. You have to sort of keep the gradient actively on the whole time in order to have the effect of just an instantaneous RF pulse, almost instantaneous RF pulse. But if we look at the signal down here, then what's going to happen is you'll get, so this is, the gradient, Gx, there's the RF stim. And this is, RF record. So now what will happen is pretty much the same thing like you would have with spin echo. So what's going to happen is you're going to get rapid decay away of the signal because you've got the gradient on, and then you'll fix the signal, and the signal will get up to where it would have been with T2 star, and then it will be damaged again, and then now we'll put the gradient on the opposite way, like that. And so now we'll sort of mess it up in the opposite direction, because why are we doing that? Well, this one is canceling out, this guy is canceling out the damage we did over here. So this guy, cancel that half there. And so then, when we get down to the end here, then we'll go up again. And then we'll, be damaging it the other way, and then, eventually, so you can just keep going, doing that again and again. So then right over here, you'll expect there'll be another little echo. So they'll get smaller and smaller over time. So, at the beginning, they're really big, and then they get smaller, and then they get, big again, and then they get smaller, and a little bit smaller this time. And you got smaller this time. So you can do a long train, a train of echoes, and that's exactly what's done with EPI, the standard kind of scan you would do for functional MRI. You would do a whole bunch of these, and how many of these would you do? You might do, like 64 of these or 100 of these. So you do like a whole pile of them, a lot of them. So one of the things that's important to keep in mind is kind of what is the scale of this. So if we draw the regular kind of FID, like where it's free induction decay, which means we didn't turn on a gradient, we didn't do an RF, didn't do anything. So our regular free induction decay might look something like this. So this is T2 star. So here's our regular free induction decay. We do one RF. So that's the result of one RF, and it's not supposed to go up. It's supposed to keep going down. Okay, so that's, e to the minus t over T2 star. So if we did another spin echo, you could get back up to a higher curve, which was the T2. But that's the basic free induction decay of just looking at what happens when you do 1 RF. So if we do EPI, what's going on here? Well, we're actually cramming in 64 echoes to this thing, like this. So what's actually going on is, here's that curve, because that's the curve that this is the, I forgot to draw that in. This is the, e to the minus t over t2 star curve that you're getting up to. So here's that curve that you're getting up to, like that. Every time you fix the damage from your gradient. And so for something like an EPI scan, there'll be 64 echoes in just in the space, this little space. So what does that look like? Well, you'll slam the gradient on and shove the signal all the way down to nothing, and then it'll come back up again because you reverse the gradient, and then it'll go back down again, and then come back up again. So there'll actually be 64 echoes in here. So there'll be a lot of signal, then no signal, a lot of signal, no signal, a lot of signal, no signal. So that would be, what an EPI scan looks like. So the whole thing, all these echoes would be all squashed together just into the space of a single one of these decays. I just drew 4 here, but you could put 100 in there. And that's why the magnet makes such a high-pitched beep, because what's happening is the gradients are going back and forth like 1,000 times a second. So very rapidly, because they have to collect all the data before the T2 star decays away, because there's no spin echo, so T2 star is it. You're just that's as much as you're gonna get. So that's gradient echo. So one of the things about gradient echo, the reason it's used for typical functional MRI is because we're actually trying to record the effect on the magnetic field of the blood oxygenation, which is a T2 star effect. So the blood oxygenation changes the local magnetic field, slightly changes the local magnetic field, also known as the T2 star effect, the star part of the T2 effect. And so in order to actually get functional MRI data, we have to have a gradient echo, typically have to have a gradient echo scan. If you do a spin echo scan, it's going to cancel out the bold effect, and that's definitely what occurs. So if you do a spin echo instead of a gradient echo, you can basically mostly make the bold signal go away. We'll talk a little bit later on about how you might want to use spin echo, a tricky way of using spin echo to do functional MRI, but for the most part, functional MRI will be gradient echo because we're trying to record this large blood oxygenation effect on the local static magnetic field. And so, we say static, well, yeah, it's changing over a second. That's what we consider static. What we consider not static is like oscillating protons that are oscillating at 123 million cycles per second. That's not static. Okay, so now let's completely change gears and talk about stuff that's on the homework. So what we're doing now is just looking at the very beginning of contrast and contrast between different tissue types. So what's this absolutely simplest thing you could do? Now, the absolutely simplest thing you could do would be to have an RF pulse and just repeat it. So we do an RF pulse, and then we just wait a certain amount of time. So we just wait that amount of time, and then do it again. And then we just wait that amount of time and do it again, and so on. So make that accurate. So we just do And let's just say we do, just for simplicity, we do a 90-degree pulse. You'll see why this makes it a little easier. So if we do that, then we can define this time as TR, which just means sort of time of repetition. So here's the, there's RF pulse 1, 2, 3, 4. So that's the very simplest thing. And so what we want to do now is use the block equation. Use the block equation to calculate what the magnetization is going to be, the longitudinal magnetization. So that's the equation that we're going to write down here. So we're just considering the longitudinal now. We'll get to the transverse in a little bit, but so here's the here's the longitudinal magnetization graph. So this is time here. So right at this point, we're assuming, the other thing we're assuming is long time here. No RF. So we waited a long time and didn't turn the RF on at all. And so what that does is that will essentially bring us up to the equilibrium longitudinal magnetization. So this is, magnetization longitudinal going in this direction. So how much are we going to have? We're going to have whatever. Remember what that equation was. That equation was just the number of spins in the Tesla. So the amount of magnetization you get just depends on how many spins you have and what Tesla you have. And so it's basically just however much stuff you got in the magnet, and that's going to be the magnetization zero that you get. And so so what happens then? So now we shove the magnetization down to 0 because what have we done? We've if we draw the z-axis up like that, we started off with our MZ0 and we did a very short RF pulse, and the RF pulse is going to this is a 90-degree RF pulse. It's going to completely get rid of the transverse magnetization, completely get rid of the longitudinal magnetization because there's no more z-axis, and it will turn it all into transverse magnetization. We're not graphing that transverse magnetization. What we're graphing is what is the longitudinal magnetization as it recovers. And so what will happen is, at this point, there'll be some recovery. It won't recover all the way, because we're assuming that our TR is, say, for example, 1 second. So if we let the TR be 20 seconds or 5 seconds, 5 seconds is enough at 3t. If you let it be 5 seconds, then we'll recover all the way up to MZ0. But if we do it like 1 second, we're not going to recover up. We'll actually recover up even a little less than that. Let's make it a little less. So we'll recover up a little less than that, something like that. That's more close to reality. So now what happens, we do another RF pulse, and so we go back to 0. And it turns out in this very simple case, if we make the assumption, unwarranted assumption as we'll see, so we're assuming, here's what we assume. So we assume that there's no, start at MZ0. That means a long time before there's a long time without RF pulses, and we're assuming that the MZ is 0 after pulse. So what does that mean? That means perfect 90. So that means this here. So there's no There's no mz. Mz is equal to 0 after the pulse. So if we assume that, then we get the very simple equation. And the simple equation is an equation for how much magnetization is recovered at this point right before we do the next RF pulse. Because it turns out in this kind of setup, what will happen is this curve will always be exactly the same each time. I'm trying to make it look the same. And so we'll be in a steady state. So we'll be in a steady state pretty much at this point, right before we do the second pulse. And the equation will be exactly the same for each of these recoveries if we make these assumptions. So what is the equation? Then the equation is our standard block equation for recovery. And the way I've written it in the notes, I wrote it out as, mz at the nth pulse. So because sometimes we're going to see if you do multiple pulses, it's not the same after the first pulse. So mz at the nth pulse and at 0 minus, which means like right before the next RF pulse. So what does that mean? That sort of goes to this point right here. So right before the pulse. That's what the 0 minus. 0 plus would be right after the pulse. And so what is that equal to? That's equal to mz0 after there was a long time with no RF. And then just our block equation recovery. And the block equation recovery is 1 minus E. And instead of minus T, we're going to put in the amount of time that was recovered. So it's TR. So this is insert for T. So it's going to be TR over T1. So that's the basic block equation. And then there's another part of the block equation. Remember, there was the amount of magnetization that you had just after the pulse. The amount of longitudinal magnetization you had just after the pulse. That was in the differential equation. That was one of the conditions, one of the initial conditions that we were using in our differential equation, and that was also multiplied by, so I use the minus here. Make sure you get that minus the same thing, minus TR over T1. But we just made this assumption right here, and so that means we can cross this guy out, because we're assuming we have a perfect 90-degree pulse. So this is our end result right here. That's our end result. Now, notice what happens right after the pulse. So right after the pulse, actually, what we've done is we've taken the amount of longitudinal magnetization that we had. It was a little less than mz0. If this was mz0, it was like a little less than mz0. And we completely turned that into transverse because we're assuming there was no decay during the RF pulse because the RF pulse was so short. And so what that says is, our mz just before the pulse is going to equal our mxy just after the pulse. And this you could put a prime on there because this is the rotating coordinate system. So we've given up on all the rapid oscillations. We're just considering in the rotating coordinate system as if these magnetization arrows were stationary, more or less stationary. So basically what that says is that the transverse magnetization we're going to get is going to be equal to this mz0, 1 minus e to the minus tr over t2 over t1. So that reiterates a point that we made earlier. How can you record t1 when t1 is too slow? The change in the regrowth of t1 is way too slow to generate a radio wave that you can pick up with the RF coil, the radio frequency coil. And so how do you record T1? You record T1 because you turned in, you essentially turned your partially recovered longitudinal magnetization into transverse magnetization that you can recover. So that's fundamentally how you get a T1 signal. So that's the basics. So that's the absolutely most basic thing we can do, and absolutely most basic way that we can apply the Bloch equation. So this came directly from the Bloch equation. It just says, what's the rate of recovery of, what is the rate of recovery of longitudinal magnetization? Well, it just depends on how much you start with, and what is the time constant of this particular piece of the brain or the piece of the sample in there. That's the main thing that controls it. And then the amount of time that passed, which is the TR, that controls it too. So that's the basic plan. So it's very simple, nothing complicated there. But if you've ever done fMRI, you know that this equation is wrong. So why is this equation wrong? So let me put this arrow goes like, here's what happens like right after we did the RF pulse. Because now what's happened is we've turned all the longitudinal magnetization, which we haven't graphed. So we haven't graphed so here's M transverse going that way, and this is M longitudinal going that way. So we haven't graphed the transverse. I wrote it out here. So this is, this guy is recordable. Recordable. So, so you know that this isn't true. That's what I was saying. So why isn't this true? Well, if you ever do fMRI, one of the things you do is you always know that you have to throw away data at the beginning of a scan. So if you usually throw away, like, say, 8 seconds of data at least, so you might, if your TR is 2, you might throw away four images. If your TR is only 1, you might throw away like 8 images typically. And that implies, why are you throwing those away? Well, they're too bright. Why are they too bright? By this argument, they should all be the same. Here's the first one, that should be the same as the second one, should be the same as the third one. So, turns out that's not the way it is. And why isn't it that way? So, the reason it isn't that way is because when you actually look at the way the RF interacts with the head, the actual flip angle that you get is actually varies across the head a lot. And why is what's the reason for that? Part of the reason for that has to do with the wavelength of the radio waves. So the wavelength of the radio waves is inversely proportional to the frequency. And so as you make the frequency higher and higher, the spacing between the successive wavefronts of the radio waves are narrower and narrower. And so what happens if you, at say a half a Tesla, the radio waves are really big, like 5 feet or something like that. The crest between the successive waves. And so as compared to a head, those waves are sort of, very large relative to a head. As you get up toward 3T, they start to get smaller, and at 7T, they get closer to the size of the head. And so what can happen is the radio waves can sort of start bouncing around inside your head, a little bit like a hot spot in the microwave. It doesn't happen very much at 3T, but it happens enough that you can have like about a 25% variation in flip angle. So how do you actually determine, so, how do you determine the flip angle? It turns out it's determined empirically. One way of determining what a 90-degree flip angle is just do a bunch of flips and find out which one gives you the biggest signal. Because you can only record transverse, and so if you just do a flip that's like, about like that, the signal, will go up. If you do a little bit more, it goes up a little bit more, it starts to go down, and then you can say, that's 90. And so what are you doing there? You're actually sort of estimating across the entire head what is the biggest signal. But that doesn't mean that the flip angle in different parts of the head is exactly the same. And in fact, it could be as much as 25% off. One part of the head might be 25% over-flipped, and another one might be 25% under-flipped. So there's kind of like a big variation in this. And so then this simple argument won't work. So let's just draw out a more complicated argument for how we can sort of see why it might eventually settle down to a good signal. So let me do I think 1, 2, 3. That's good. So here's nice arc all on the board. Yeah, that's good. Okay, so now let's say we start off. So say here's our MZ0 up here. And so if we do a flip, so this is point number 1. So we do a 90-degree flip, but it turns out in this particular part of the brain it isn't exactly 90 degrees. So let's say it's about like this. Not an uncommon error. So it's about like that. Okay, so that's time point 2. So that was our attempt at a 90-degree flip. So it actually wasn't a 90-degree flip. So that means that, back here, this is the amount of longitudinal magnetization we're going to have. We're going to have a whole bunch of transverse. So, here's the transverse right here, MT. It's this. But we're going to have some ML also. And so what's going to happen, we're going to recover from this point, and say we'll recover up to like about here. So recover up to about there. So that's time point 3. So now we'll do another flip. So when we do that flip, that guy's going to sort of go down like to about here. So now what's going to happen? We're going to have a little less longitudinal magnetization to start with. So here, that's the amount of longitudinal that we'll get. So that's time point 4. And so now we're going to be starting a little lower. So here now we're starting down here. So we're starting a little lower, and so we'll recover up a little lower. So we'll recover up to something like that, and then we'll keep doing that. So we'll flip again, and so we'll get a little less, but you can see that it's getting smaller and smaller. So next time, this guy gets smaller and smaller each time we do that. And in particular, this distance right here in longitudinal is definitely less than this distance up here. And so that's a good thing, because what happens is this one eventually gets very small, and then we get back to a steady state. So after a long time, eventually we get to pretty much the same thing. So every time we're going down here, we'll end up sort of recovering up to the same point. And so that's going to take like 10 seconds, at least 10 seconds to sort of get to the steady state. So at this point we have steady state. We could do this with equations, but you can sort of graphically see what's going on. So that was 4, and then we ended up with 5 here, and then 6, and then 7, 8. We're all about the same. So a little more complicated equations than this. We would have to sort of plug them back into each other a couple times and do some cosines and sines. It gets gummed up, but you can sort of see the argument graphically what's going on here is you quickly reduce the total amount of the decrement in recovered longitudinal gets less and less until you finally get to a steady state where you're always going up to the same spot. You're starting from the same spot and going up to the same spot. And so why is that important? Well, sadly, fMRI is an extremely low signal to noise technique. So fMRI, unfortunately, very low signal to noise. So what are some examples? Well, your heart beats. You've got the heartbeat in there. So when the heart beats, it delivers oxygenated blood. That changes the signal a lot, like maybe 1%. That's like something like a 1% change in the signal. You're breathing. Well, as you breathe, oxygen comes into the bloodstream. That changes the oxygen signal. You've got movement. If you move, you might change what's in a voxel and change the signal. That could easily be 1%. The breathing could cause some problems. There's movement. There's pulsations of the brain. Every time the heart beats, the brain not only gets more oxygen, but it actually moves a little bit. That could easily cause a 1% signal. This is somebody who's extremely still. And what are we actually looking for? Well, we're looking for some cruddy cognitive signal that could be like 0.1%, or sometimes 0.05%. That's a typical cognitive subtraction signal, tiny, tiny, tiny signal. What are the differences we're talking about here? We're talking about like a 20% brightness change. So this difference here from, say, 20%, from first until steady state. So obviously we need to get rid of that because, this is 20 times or 100 times bigger than our cognitive signal. So that sort of introduces you to the dirty secret of functional MRI, which is that we're working with these tiny signals that are so close to the noise. They're right in the range of heartbeat and movement artifact and pulsations of the brain and breathing and all those things. They're actually smaller than those signals. They're smaller than those signals, so that's why you have to record a lot of data in order to pick up these tiny FM. These are, an fMRI subtraction. That's the kind of signals that you're getting. So that's why it's really important to sort of pay attention to these different features that essentially make the signal a little bit unstable or slightly changing over time, because we're trying to pick up these ridiculously small signals. Okay, so I think we'll stop the recording there, David.